Okay. Oh, yeah, that's right.
Is it just one page, maybe?
No, it's,
No, I'm wondering if
maybe
he
this.
exported it as one. Aha, that looks better.
It does. Why did that do that? Okay, sorry. And just check all the files are there, or all the slides are there. Yeah, they're all there. Okay, thanks.
I think if you outside the box.
And you need to zoom out. No, there's two of them.
Or click up.
Command minus. There you go.
Aha.
Now ask me for share.
Woo!
He's going to ask. And we're ready to go.
Okay.
All right. After a 2-minute launch today, we are ready to rock and roll. Let me welcome Kevin, who will be here with us in the room to represent Project Callisto, an extraterrestrial collaboration with WebRTC and AV1. If you're in this room and you are part of the RTC Web Working Group, raise your hand. Okay, so several people. Cool. Other codec and other friendly people here. Take it away.
Great. Thanks, Ted. It's an honor for me to be here speaking to all of you esteemed Internet Engineering Task Force members. Thank you for having me. I'm Kevin. I'm with Cisco, and I wanted to share with you a brief version of the story of how we came to participate in Project Callisto. We partnered with Lockheed Martin, together with other companies in the industry like Amazon with their Alexa technologies and Apple iPad technologies to try to solve the problem of real time, or as real time as we can do, given the latencies, communications in deep space exploration. And I want to give credit to the folks who worked on this implementation and built the original version of this presentation. I'm just here to share it with you all. So what is Project Callisto? It's a technology package on board the Orion spacecraft to test the viability of commercial technologies in space exploration. And I mentioned those technologies already as WebEx by Cisco, Amazon Alexa, an Apple iPad tablet mounted inside the Orion spacecraft to allow future manned or crewed, excuse me, crewed space missions to collaborate in near real time with folks on the ground. And Orion is the deep space exploration spacecraft built by Lockheed Martin. And Artemis is the series of missions to fly that spacecraft to the moon and ultimately to land on the moon and to perform moon exploration and ultimately Mars exploration. Okay, sure. Thank you. You can scan that QR code up at the top if you want to learn more, or go to that URL and it's in tiny font up in the top right-hand corner, lockheedmartin.com, and find the Callisto page there. So Artemis 1 is the first of the Artemis missions that will launch from Kennedy Space Center now targeting November 16th launch window at 1 a.m. Eastern time. That's 6 a.m. here in London for those of us that live here. And it will circumnavigate the moon and return to Earth as a test flight of this system. We're all super excited and crossing our fingers that that November 16th date holds. They've been monitoring the hurricane weather, and they've had a few resets on the calendar, but November 16th is the current scheduled launch date, so we'll see if that happens. And the challenge that we were asked to solve is real-time video HD collaboration in space. And there was, as you can imagine, a few technical challenges. The first one is it's a long way to the moon. You know, our industry standard is 300 milliseconds round trip for real-time collaboration. With Project Callisto, we were asked to engineer it to up to 20 seconds or 20,000 milliseconds round trip, which is an awfully long time in the world of video communications, as those of you who work on video know. And if you want to see what 20,000 milliseconds looks like, oh, this is not a build slide. I lost my builds because I converted it to PDF. Never mind. The PowerPoint version, that line draws out over 20 seconds, so you can kind of experience it. So obviously the questions are we going to have delays in the various protocols, not only at the video bitstream layer in our AV1 codec, but also in protocols, you know, setting up signaling, you know, connecting the call, etc. And how effective are our error resilience and recovery techniques going to be in the face of these huge latencies and packet loss and jitter? Thank you. I've got 7 seconds remaining. What does that mean?
I started at 20 seconds.
Oh, thank you, Ted. Okay, thank you. Yeah, do that, do that. Okay, well, there we go. So this is how long it takes to send a video frame from the Earth to the moon lander and respond, right? Awesome. Thanks for the demo, Ted. So the second problem is the satellite network has packet loss and jitter and very low bit rates. So it's an asynchronous network of 200 kilobits per second upstream from the ground to Orion and 1 megabit down from Orion to the ground. And of that 200 milliseconds, 160K of that is video and 40K of that is audio. So, you know, that's a challenge. How do we get high definition 30 frames per second video to work at 160 kilobits per second? And there's also packet loss and jitter to contend with. The third problem is the first Artemis mission, Artemis 1, is an uncrewed flight. There's no humans on the thing to touch the iPad and launch the app and place the call and all of that stuff. So how in the world are we going to solve that? You know, how are we going to launch the application? How's the application going to know when to join the call? How, you know, what happens if the app crashes? What happens if a pop-up gets in the way of the application? And so there's nobody to touch it, and there's no, you know, we couldn't use audible commands either because our system is the thing that is receiving audio from the ground, playing it out of our speaker on the iPad tablet, and then, you know, we could try to loop that back into the microphone, I suppose. But like, what we would have to have a call up in order to have that pathway established. So like, so we had to come up with clever technologies for that, or clever techniques to solve that problem. So our solution was to build a custom version of our WebEx app, highly customized for this mission. And we built a new protocol translation server that sits on a container co-resident with our conferencing server on the ground that we called the ground control server. And we implemented a new UDP-based signaling protocol that gave us a single round trip transaction request response to join the call, eliminating all of the normal TCP and TLS handshaking and multiple round trips to get a call up. And that protocol converter simply converted that new UDP protocol that we implemented to the normal standard WebRTC HTTP WebSocket based communications protocol that we do normally on our server for our normal application. And we set up a simulated network of 20 milliseconds of latency and packet loss and jitter. And surprisingly, it just worked. Like out of the box, we were shocked. Except H.264 video codec kind of fell apart at these low bit rates and looked pretty bad. So we introduced AV1 into the project, which we had wanted to do, but we tested it with 264 before moving forward with AV1. So we said, yep, okay, confirmed. 264 is not going to work. Let's go ahead and implement AV1. So just a few words about AV1. I'm sure many of you in the room are aware of it, and many of you, I'm sure, have contributed to it. But AV1 is a new video codec designed by the Alliance for Open Media, which was sponsored by several companies, but 3 of those were Google, Cisco, and Mozilla, contributing our respective video codec technologies into this effort to produce a codec that would be as good or better as H.265 while being open source and royalty free. And you can read more about it at the, you can read more about our contribution to that at that link down at the bottom. And I just want to shout out Jonathan Rosenberg in the room here for initiating and leading this effort when you were at Cisco. Thank you, Jonathan. So we have our own implementation of the Cisco AV1 codec, and that's primarily because the AOM version is not super optimized for real-time, low latency, bidirectional video conferencing, real-time communication. So we have our own implementation of the AV1 encoder developed by colleagues in UK, Norway, and China, and highly optimized for real-time latency sensitive communications. For decoding, we use the open source David decoder from Videoland that was adopted by AOM. And that gives us these, our implementation gives us about 30% better compression or 30% less bitrate at the same complexity or the same CPU consumption as our reference OpenH264 codec that we publish and lots of other companies use. And we've integrated AV1 into our WebEx product in WebEx meetings. And we also implemented it into this custom version of the WebEx app and the server, the conferencing server that we created for this Project Callisto. So what were the challenges and solutions at the video codec bitstream level that we had to solve? So first of all, it had to have great quality, or at least good quality, at extremely low bit rate, 160 kilobits per second. And to solve that, AV1 itself has inherently in it, lots of tools and techniques for getting pretty decent quality at very low bit rates, like quad tree super blocks and context adaptive entropy coding and various other techniques. So we employed all of those. Second challenge is the huge latency, up to 10 seconds in each direction. So obviously, packet loss, requesting a keyframe is not going to work. So we just simply ignore keyframe requests and we generate keyframes periodically. And then there's packet loss. So we implemented normally, and I really enjoyed Luke's presentation earlier about quick over media. So if you guys attended that this morning, then you remember the IPP or IPBP, GOP structure that Luke talked about. So we implemented a broadcast-like GOP structure with discardable P-frames, and to make it more resilient to packet loss. And then the problem of keyframes being traditionally very large and subject to being corrupted by packet loss in transit, we downscale half the resolution, then encode and then upscale on the other end when we decode. And we also allow the quality to kind of build up over several frames if there's not a lot of motion in the video. And the server and the app switch between normal mode and this error resilient mode described on the right-hand side of the slide based on the frequency of IDR requests. So if we start getting IDR requests, we switch into this resilient mode, and then we switch back out of it to try to increase quality when IDR requests are not coming through. So we ignore them, but we still get them, and we switch into this mode when as needed. So lastly, I'll just say that the no touching and no audio interface, the solution to that was a custom like MDM-like thing that's sort of like just a URL that says, you know, push this URL to the OS and it will launch the app, and then we just automatically join a predetermined meeting URI. So that's how we solved the no interaction problem. And I just wanted to close with giving credit to my colleagues who contributed to this. I was the director of engineering at the time, and Thomas and Dimitri and Alex on our team worked on this together with many other engineers at Cisco and our colleagues at Lockheed Martin. So just wanted to say thanks to all of them for making this reality, and fingers crossed this thing launches on November 16th. Thank you for having me.
The queues are open, so if you can, please use the tool. I realize it was a little bit hard for people because of the URL problem on the agenda. But if you can't get into the tool, you can get in line and we'll recognize you anyway. But if you could use the tool to form a queue, that'd be great. Darren Dukes, you're first.
Yeah. So what was that user experience at 10-second delay, you know, in one direction? Is that going to be a usable thing from when you tried it in the labs?
We did, yeah, that's a good question. It is, you know, to be honest, it's a bit of a walkie-talkie kind of mode. You certainly can't interrupt each other like you can on a normal video conference. Even in normal video conferencing, interrupting is, you know, you can accidentally step on each other because of the end-to-end latency. Here, that's just exacerbated, right? That you really need to kind of wait and let them finish talking before you try to speak over them. But other than that, it works great. And it's not just video, but it's also real-time whiteboarding and content sharing. I should have mentioned that in the presentation. So imagine, you know, we could draw together. It would take a while for what you've drawn to show up for me and what I've drawn to show up for you, but it works.
So in those space movies where they've got, you know, something's gone wrong and the engineering team's figuring it out, they could like whiteboard the solution.
Exactly.
In somewhat slow real time.
Exactly.
All right, thanks.
Thanks.
Hang Sure?
Yeah, Han from Huawei. I think that you choose AV1 over H2264 because it's very efficient, right?
Yes.
Yeah, but H265 is also very efficient. So what's the benefit between AV1 and yeah?
Yeah, I think from our perspective, and I don't know that everyone in the industry shares this perspective, but from our perspective at Cisco, the challenge with H265 is the patent challenge, right? So for us, AV1 is open source and free to use, and so it makes sense, even if they're roughly equivalent technically.
Thank you.
Jonathan?
Yeah, I can't, I've tried a million times and I can't get on the on-site queue, so I apologize. Jonathan Rosenberg, super happy to see this. This is awesome. Normally there's a trade-off for video encoding between computational complexity and bandwidth. And so to get the bandwidth down, you know, you could do a lot more work on the encoder side. Did you also have computational constraints? Because computational complexity leads to, I guess, weight or power or something that are all considerations in the moon. So what's the compute environment here?
That's a good question. I don't know the details of the Apple iPad because It's an Apple iPad mounted inside.
Oh, I
the
missed
Orion
that. It's
capsule.
literally an iPad.
It's
on
literally
this
an
thing.
iPad Pro
I thought there was some
mounted
super
to the
fancy,
dashboard
like.
of.
Then I withdraw my question. All right, thank you.
Yeah, it's a very customized version of our iOS app running on the iPad.
Darren?
Yeah, so just maybe one more with the protocol that you'd invented, the UDP based one
Yeah.
to get to the spacecraft. Do you see? Are there any advantages to that? Did you kind of discover anything interesting with having to come up with that? Is it usable outside of this use case?
That's a great question, actually. I guess from our perspective, we didn't think that it was usable outside of this very constrained use case because, we basically are doing, we disabled SRTP, we disabled TLS, so not the kind of thing we would normally recommend, customers to do. So it was very like purpose built for this closed network system where confidentiality and data integrity and all that are less of a concern.
Okay. And there was a previous group of BOF that I was in where we were talking about, low power stuff and, particularly things that were time sensitive as to how much bandwidth was available and whatnot. It'd be kind of interesting if you were to build up from what you got to with that and minimally add back to it what you'd end up with that could be very low bandwidth, but still have that high quality in order to reach those kind of rural areas.
Yeah.
That maybe aren't in the moon, but
Yeah,
that
yeah.
maybe feel like the moon.
That's an
sometime.
interesting question. Yeah.
Thanks.
Yeah, because I do think that there's a huge opportunity there in like, remote farming communities or other places where you're,
Yeah, exactly.
near Earth orbit satellite networks and being able to do really low round trip transmission communications. Yeah. It's
Yeah,
a
I
good
mean,
idea.
I'm from more northern-ish Canada, not very northern Canada, but yeah, once you get outside of the cell ranges,
Right.
There's not a lot of bandwidth.
Right.
So, okay, great. Thanks.
Yeah. Thanks. Okay.
Alyssa?
Hi, Alyssa.
Hey,
Nice to see
good
you.
to see you.
Thanks.
Can you talk a little bit about the limitations in terms of the features and conferencing? Like, could you have two people on the ground joining a conference with the moon?
Oh,
like
yeah.
in terms of our normal typical experience of video conferencing, like what's available in this context versus what we are accustomed to as terrestrial users of WebEx?
I love that you asked that question because I should have mentioned it on the slide, but because I lost the build, I kind of maybe missed some points. So on the ground, they have normal WebEx devices and like our board and our room systems and our desktop systems, like the Desk Pro, for example, and they're all connected in a conference with the Orion spacecraft, right? So they can all have be having a real-time meeting, and the application that I believe NASA wants to use it for is to invite students, kids, other people from the public into their ground control facility to experience this and actually collaborate with astronauts, which is pretty cool.
Yeah, that's awesome. Thanks.
Juan Carlos?
Yeah, hi. Juan Carlos Zúñiga. So I was curious because this is definitely very interesting first use case. And looking into the future, we probably will face situations where we will not have line of sight, right? Because this is the first time to the moon. The
It's
bright
going
side
to go around
of the
the
moon,
backside of the moon.
go around, and even further into the future. We
Right.
can think of Mars, and that's when normally LEO and stuff like that
Right.
will come into picture so that we can work when there are situations when there's no line of sight, in which cases most likely there will be satellite relays.
Right.
So have you thought or do you have any idea, in this case you showed the architecture showing the proxy, how you simplify the signaling onto the space station, but if ever we put more relays or an LEO satellite network, would that also work? Or have you guys thought about that multi-hop architecture?
That is a really good question, and we didn't, because we didn't actually have a lot of detail from NASA about the the inside details of how their network works. But it is a satellite relay-based network, which is why the latencies are up to 20 seconds, because the average distance from the Earth to the Moon is much less than 20 seconds. It's like 3. But they said you need to engineer it for up to 20 seconds, and that's because it's going to be bouncing off these satellites when it's like on around the backside of the Moon. It has to hit a satellite before it comes to the Earth and so forth. So, but I'm not as familiar with the the underlying details of how that satellite network works and what we could do to optimize it further. So
Okay,
we'd have
so
to look
there's
into it.
already multiple relays,
Yeah.
extraterrestrial
Yeah.
relays.
It goes from their near Earth satellite network to their deep space satellite network as it goes out,
Okay.
further away to the Moon. I think it switches to their deep space network.
But you don't know how many hops to
I
go.
don't know how many
Okay.
hops.
Okay.
No.
Maybe. Okay.
Yeah.
Thanks.
Yeah. Thank you. You just answered my question, because I was curious how the 20 seconds do come into place, and
Right.
how they would decompose given the architecture you showed in the beginning.
Yeah.
It's multiple relays. They are further out and bridge large distances, and there's just not an easy shortest path.
Yeah, exactly.
Okay. Would there be any details on that available at some point?
Sorry?
Would there be any details on that structure available at some point? I'd just be curious.
Yeah, we're super curious too. Those details would have to come from Lockheed and from NASA. We were asked not to. I mean, didn't share. It was sort of like they shared with us what we needed to know and nothing more.
Yeah. Okay. Understood.
And I had to get permission to give this presentation, because even this amount of detail is more than we had previously disclosed in our respective marketing announcements and stuff. So I had to go to them and ask for permission to share this with you.
All right. Cool. Thanks.
Yeah.
Yeah, John Lennox, like maybe, when your comment about that tells me, someone asked my question. I was going to ask, you mentioned you disabled all the TLS and SRTP. Was that just for practicality, or was that a policy like, we want, people on the ground, other people on the ground to be able to watch it live, or?
No, it was that's a good question. The disabling of TLS was for practical reasons, to eliminate the multiple round trips and eliminate TCP and go with UDP. But for SRTP, that was simply a convenience thing. That's like, well, we don't need it. It's in a closed, almost like a closed circuit television kind of network. It's not connected to the internet at all.
I'm just wondering, and if you had any thought, maybe this isn't directly what you're working on, but had any thoughts, like if you did need to encrypt it, how would you do keying when you have a 20-second latency?
Yeah, exactly. And like rollover counters
Yeah,
and stuff like
exactly.
that come into play, right?
Yeah. Did you have any thoughts about that, or just you turned it off and
we didn't think through that
Okay.
very hard. We're just like, oh, we don't need SRTP, we'll just disable it, and then so therefore we didn't have to worry about rollover counters.
So we'll point out that if we were doing this super quick, you could do zero RTT resumption if you started the sessions before they left the Earth. then you'd always just be resuming something that you already had set up with the tickets. Anyway, Mo.
Yeah, sorry, Ted. Something's wrong with the in-room tools, not letting a lot of people in. So
yeah, if
just
I
coming up
wasn't
to the
clear
mic
about that,
anyway.
if you can't get into the tool, you can get in line, and we'll just recognize you from the line. Sorry about that.
So Mo Zanatti, just wondering if so this was obviously for converse or for human-to-human use, but I assume that there's a lot of video, from telemetry systems coming back, and maybe even robotic control that's delayed. A lot of autonomous within 20 seconds, but maybe human controlled beyond that.
Yeah.
Is some next steps to maybe think about broadening this to use this core real-time communication technology to go
Enable
across all
other
the video
things.
feeds, or even any sensory feeds, not just the video, but any kind of sensory data that's streaming back to ground stations, and then maybe something that has a 20-second, reaction time that could usefully feedback and change the sensory systems. Is there any future work to look at doing something like that?
I don't know. We had speculated on some things like that too. Like, for example, somebody on the ground could say, hey, Alexa, turn the lights on or turn the music up or whatever to the Alexa that's running in the Orion spacecraft, right? and I don't know if this is true at all. This is a total rumor, but I thought that I understood that they also had a GoPro mounted inside the spacecraft pointing at the iPad so that from the ground they could see what's being displayed on the iPad. So there are other systems, and then I don't know about the actual spacecraft itself and all of the telemetry and instrumentation and all of that on the spacecraft itself. I have no idea.
But this was human to human intended communication?
Right.
Okay.
Hi, Don Fedek. While you were talking, I wondered, I know some of these WebEx and things have the ability to do closed caption real time. Do you use the closed captioning in real time? Did you try doing that? Because I think that'd be quite useful because of the time delay, being able to refer to the text. So
That's a fantastic question, and there's a challenge with that, which I can't speak to authoritatively because I'm not on the Amazon Alexa team, but they had the same challenge, is that, normally the device is able to interpret the wake word, but then all of the actual, automatic speech recognition and all of that stuff is done back in the cloud. Well, this system's a closed system. There is no cloud. There is no back end. So they had to build a custom version. My understanding is Amazon had to build a custom version of Alexa to do a lot of that locally. And we would have the same problem within the WebEx app. Is for real-time closed captioning and real-time translation, we rely on back-end systems to do all of that, ASR and text-to-speech and natural language processing, NLP, and so forth. All of that would have to be built into the app itself or into the server on the ground and not connected to the internet. And all of those dependencies would be the challenge that we would need to solve. Maybe in the future mission, they'll ask us to work on that.
Any other questions? So I'll take a moment then to thank you again. And I have to say, I'm going to reveal myself as there's somebody coming to the queue now. just speak, no worries.
Okay, sorry. I just had a quick thought. You said that the terrestrial WebEx clients were just normal ones, right? So did you ever think about relaying the cloud processing through those so that you can do all the captioning of those kinds of extra services? Because those aren't in the closed network only, right? I imagine they're kind of dual homed.
So they are on the closed network, my understanding. So I think the entire system is not connected to the internet is what I was led to understand.
Oh, okay.
So I think it would still be a challenge but yeah, if you could, if those could be dual interfaced with one leg in the NASA network and another leg connected to the public internet, then absolutely, we could do something like that.
Yeah.
Yeah.
Okay. All right.
I can't remember whether it was in your slides, but do you sort of look at FEC for some of your transmissions? Because it seems like a kind of useful thing.
You're right.
Given that you can't do ARQ for.
Yeah, you're right. That's a very good question, and we should have. We did not use FEC just for this simple fact that we didn't implement it in that custom version of the app. But you're right. In normal WebEx, we absolutely use FEC, and we also use now RTX retransmission. And in combination. So like we can dynamically switch between forward error correction and RTX retransmission, and we can FEC protect the RTX packets so that the retransmissions have a higher chance of getting through. But we didn't have all of that in this custom version of the app. So, but yeah, maybe a future version of it, if NASA asks us to be a part of Artemis 2 or Artemis 3, maybe we'll do that. Because you're right, FEC would definitely be useful.
I guess it's sort of to drive that potentially, one, it might be useful to understand what the sort of loss patterns are around the transmissions and what drives those, whether it's solar storms or
weather,
some other kind of, or some
right.
other kind of space weather, that then you could maybe alter the level of FEC that you're using depending on whether there's a sunspot or something like that.
Yeah, yeah, you're
anyway,
right.
Yeah, okay.
Okay, so let me say thank you, and let me also say this is a wonderful blast from the past for me. My very first IETF, I was here as a representative of a contractor to NASA, helping out with the very early days of the web. So seeing this work come here and get talked about, picking up some of the work that was done here in WebRTC, some of the work that many of the companies here have contributed to in AV1 and AO Media. It's really great to see how far we've come and how close it looks like the experience they'll have in Artemis 2 and 3 when they become crewed missions to what we can give our customers. So that's great. Thank you very much for coming.
Thank you, Ted.
That was great. Thank you very much. Well, it's been a long time since I've had to fight with lawyers this